Okay, so we're now going to illustrate some of the basic principles we did in the previous chapter, chapter 6 on quantum mechanics, using as a vehicle, as a means, the particularly simple formulation of quantum mechanics that you can get with 2x2 spin matrices and spinners, just two component vectors. I mean, very, very easy, right? So you can de-concentrate on the math and concentrate more on the physics, on the concepts, the weirdness of quantum mechanics. And it won't be in this session, but where we are heading towards the mathematical tools needed to understand the famous Bell inequalities. One of the highlights of quantum mechanics is talking about famous experiments done in the 80s, early 80s, by a French guy called Aspect, A-S-P-E-C-T, and he confirmed experimentally, in a particularly convincing way, that it seems that nature is genuinely non-local, that non-locality, or as the computer guys talk about it, the quantum computer guys, they tend to use the term entanglement, which is weird. Go back to the first lecture pretty well that I gave on quantum mechanics. Entanglement or non-locality is weird. It says that two particles can interact and then separate, but after the separation they still act as though they're a single system in some sense. They are entangled in that sense. So that when you perform some kind of measurement, you do something to one of them, that will have an effect on the other one in zero time. Zero time on the other one. So it's sort of action at a distance, instantaneous effect. The cause is something that happens to one particle at one end of the universe, and it in zero time affects the behavior of the second particle at the other end of the universe. So what does that imply? That's a fascinating question for 21st century physics and quantum theory. I'm just mystified. This is one of the research issues I really would like to get into is what are the implications of entanglement? Now, that question's been partially answered already. It's the foundation of quantum computing. Entanglement is the basis. There are two main ideas in quantum computing, two phenomena. Like, quantum computing is computing using quantum phenomena. And which phenomena? Well, two main ones: superposition. The other is entanglement. So it certainly gets used, but the nature of it, what it is, and again you come back to the old question of interpretation of quantum mechanics. Interpretation of entanglement. What is it? How does it work? How? Deeply mysterious. And I hope you as you go through these courses, especially the physics courses with me, you will catch, I hope, some of my fascination and the deep mystery of all this stuff, because it's just fascinating. All right. Okay, so let's take a general quantum state in the context of 2x2 spin matrices. We're not concerned with the motion of the particle, we're just concerned with the spin, that's all. And let's say spin measurements along a z-axis, let's say, so we're measuring spin up or spin down, that's it. There are only two eigenstates. There's the spin up and the spin down eigenstates or eigenfunctions or eigenvectors, they're all the same thing, right? So your general state superposed, you know, if you have eigenstates, you can sum them. You can form a weighted sum where these eigenstates are orthonormal. You've been through that many times. So this is to illustrate all those principles we did in previous chapter, chapter 6, in the context of spin matrices and spinners, and because it's also simple. Okay, so here's your general state for a wave function in the context of measuring the spin component along the z-axis. So here are your two eigenfunctions. So the spin up state and the spin down state, and you're taking a weighted sum. Now, these are just two complex numbers. And now you can rewrite this as 1, 0 or 0, 1. So you could just rewrite this as down here. Let me see that clearly. So, you know, this just comes C1 here, and that comes C2 here, and just add them. Just adding two vectors, right? It's like adding two matrices. So you just get C1, C2. So your spinner is just C1, C2, that column vector. So that's just psi. So you can rewrite psi, you can rewrite that as just this. Okay? Very, very simple. Okay, so that's our general spin wave function, let's say. We'll label it that. Now, remember these coefficients? Now assume that these eigenfunctions are normalized, they are orthonormal, and that you asked to do this for homework in the previous session. So assume they're orthonormal, okay? So knowing this psi, we know the 2 by 2 matrices, spin matrices for S squared and SZ, you know, the Z component of the spin, S. So we can now find the expectation values, you know, the average measured values. So let's do it for SZ and for S squared. So these are using this state. Now, of course, the expectation values depend not only on the operator, but also on the wave function. If you have a superposed wave function, you'll get a different expectation value. You would expect the average value to be different than if the wave function that you're using in calculating this expectation value, if it were, say, an eigenstate. If there's an eigenstate, you'll get you just get, well, the expectation value will just be the corresponding eigenvalue. Hope you see what understand what I've just said. Right? So let's do it for S of Z, and then we'll do it for S of Z. Sorry, S squared. Okay. So let's find the expectation value, the average measured value for S of Z. In other words, the component of the spin momentum along the z-axis. That's what this means. Right? Now this is just shorthand for this. Remember, that's where these angular brackets came from. They came from this bra operator ket notation. Right? And remember this Hermitian operator, you can put this S here to the left of the ket psi, or you can put it to the left of the bra psi. So having like two vertical lines here creates a kind of symmetry. It just looks symmetric because Hermitian, that's the property of Hermitian operators. Yeah, you can put them either in the ket or in the bra. All right. Well, we're talking 2 by 2 matrices. So now from the previous session, when you're talking spinners, how do you define the bra ket? Well, the bra then becomes the conjugate of the spinner, the transposed. So it becomes now a row vector rather than a column vector. So there's your column vector C1, C2, and here's now a row vector C1, C2, but conjugated. You know, the i's become minus i's, right? And the operator, now a matrix, 2 by 2 matrix, is h bar over 2, and this matrix. Okay, well, then it becomes trivial, just simple matrix multiplication, and you'll get this answer. It'll be C1 squared minus C2 squared, which is not surprising, right? It's the probability of it getting up plus the probability of getting it down. Does that make sense? Or should that be a minus? Maybe there should be a minus. So you're trying to find... So if it's equally likely to be up as down, then the average orientation will be 0. So maybe that... Maybe it should be a minus. I need to think about that. I find it easier to think in these terms. So, so you take the weighting of the probability that it's up, the plus values, and then the weighting of the measuring down, and if it's equally likely to be measured up as down, then the average orientation will be 0. These two will cancel out.